It's currently good morning as this has been recorded on Wednesday morning, but if you watch it during the scheduled class time, it will be good afternoon. Today we're having a virtual class, and this is just an audio overview of what you should be doing. To start with, what we'll do is I'll share the screen. And you should be able to see a screen that includes a handwritten example, which is called another example on aliasing. What I decided to do is to work a complete example showing you what effect this undersampling has on the signal you can reconstruct. I start out with a signal that we call x of t that has three components. The signal is written in the form a cosine 2 pi ft. So what that means is we can read off the frequency content. There aren't or there isn't a 2 in any of the terms. The digits there are twice the actual frequency. So what that means is we can immediately determine that there are three frequency components in the signal, and the frequency components are 1000 hertz, 3000 hertz, and 6000 hertz. That means we can immediately tell that the maximum frequency contained in the signal is 6000 hertz. Now, according to the sampling theorem, if I want to properly sample this signal, then what I would have to do is have a sampling frequency of 12,000 hertz, and then I would be able to have a good digital representation of this signal, and I'd be able to reconstruct it exactly. So that means that our Nyquist rate for this signal is 12,000 hertz, and if we wanted to properly sample it, we would sample at 12,001 hertz, or at least something greater than 12,000 hertz. Okay, so that means we've answered the first question that I asked: what's the Nyquist rate for this signal? So moving along, I'm now going to ask another question, and I'm going to say that assume that we sample the signal at a sampling rate which is 5,000 samples per second, or 5,000 hertz. What's the discrete time signal after sampling? So we've got fs is 5,000 hertz, fs over 2, which is 2,500 hertz, and that fs over 2 is sometimes called the folding frequency. It's the largest frequency that can be represented uniquely by the sample signal. If going back to the notes on sampling, I think on the first page, we relate the time to the sampling period and the number of samples. We can then write an expression in terms of the sampling frequency, and that allows us to write our sequence from our function, which I've done at the bottom of the page. Well, that can be simplified, and I just noticed an error that I will fix before I post it, because if we go back to the previous slide, you will notice that my original signal had a sine as the middle term. I got carried away when I wrote this, and I wrote it as a cosine, which I will fix before I post the notes for you. But anyway, so basically, if you can see the cursor here, this should in fact be the middle term should be 10 sine of 2 pi there. In the next line, then I did that, and actually, if I look back to my original signal, it should have been 5 times sine, and I wrote 10 times cosine at the bottom of the page, presumably because I looked at the third term anyway. I didn't get it right when I went to the next page. So you can say I just divided through. So instead of having 1,000 divided by 5,000, I've got 1 divided by 5, but that's our sample sequence. But I can rewrite that because we can use the properties of sines and cosines, and we can rewrite them, and you can see that the third term actually gets rewritten in terms of the first term. So collecting terms, I get for my expression that the sample sequence looks like 13 cosine 2 pi multiplied cosine of 2 pi, sorry, of it's 2 pi multiplied by 1/5 multiplied by n, take the cosine of all of it, and then subtract then 5 times, and again it's 2 pi times 2/5 multiplied by n, take the sine of all of that. So what this means is that in the signal that we have, only the signal at 1,000 hertz was actually below the folding frequency. So this is unaffected by aliasing. The components at F2 and F3 are above the folding frequency, and so they'll be changed by the aliasing effect. I didn't ask this next piece, but I'm going to show you that my double star equation there, which is the one above the last one, can be justified by looking at our aliasing condition. So I've rewritten our aliasing condition there. And then I solved it for a different frequency. And basically what I'm saying is we can find that alias frequency then by subtracting an integer, a multiple of fs, from the other frequency. I don't have to do it for F1 because it's unaffected by aliasing. And I do want to yield frequencies that lie in that band, and we talked about why that was a couple of days ago. So F2 and F3 will be changed. So I can find the A-list values, and the way I set this up, one of them comes out as minus 2,000 hertz, the other one comes out as 1,000 hertz. But those results do agree with my double star equation on the previous page. We also know from page 2 on the notes on sampling that we can write the frequency in discrete space in terms of the sampling frequency and the original frequency. So that means I can write capital F1 is equal to 1/5, capital F2 is minus 2/5, and capital F3 is equal to 1/5. And those results do agree with my double star equation, which was a couple of pages back. And then I ask another question. What's the analog signal y of t that we can reconstruct from the samples using the interpolation method of Shannon that we discussed on Tuesday? So since we've got the sample sequence, we can just basically use t equals n over fs, which is again from our sampling notes, to rewrite the signal, and it works out to be y of t is 13 cosine of 2,000 pi t minus 5 sine of 4,000 times pi t. That means there are only 2 frequencies present in the reconstructed sample signal, a frequency at 1,000 hertz and a frequency at 2,000 hertz. So very, very clearly, the reconstructed signal is not equal to the original signal, and the reconstructed signal yt is distorted because of aliasing due to the low sampling rate, and the moral of this example is always sample at rates that are more than twice the maximum frequency present in the original signal. So this is a more detailed example and a more interesting example than I worked earlier. I could get you to do one of these, but it would be basically the same. So just make sure that you understand this one. And as I said, though that one line where I accidentally have a cosine instead of a sine and the wrong amplitude will be fixed before I post the notes. Okay, so I'll stop this screen share and start another. Actually, I'll just go ahead and close that out. So now I'm going to start another screen share. And let's see, I've got to find the right one. Sorry about that delay. I had trouble finding it on all of the files I had open. Anyway, so this basically is the end of chapter 4. I'm not going to read this set of notes to you. It's basically the summary of the major statements in the latter half of the chapter about how we classify systems. I remind you of what the system representation looks like, and then I go through the difference between a deterministic and a stochastic system. I talk about continuous time and discrete systems, which we've done a lot. Then I remind you about systems with and without memory. I talk about causal and non-causal systems and give some examples. I talk about linear and non-linear systems and introduce some non-linear systems. I then talk about time invariant and time varying systems and talk about the differences between those. And then I point out that if a system is both linear and time invariant, we call that a linear time invariant system or an LTI system. And that's what we're going to be studying for the next 2 chapters. And then I summarize what you really need to know about stable systems and BIBO stability. So read that and read the corresponding sections in chapter 4. And they are things that you need to be aware of, but it's mainly reading and make sure that you understand what they are. So do review the chapter, and you'll notice I have omitted a few topics, and those topics probably will remain omitted for the entire course, but be sure that you are aware of the ones that we did introduce, and recognize that we did a whole lot more sampling than is in the book on this case. So I've got one other task for you. Thoroughly read the examples, both this one and last one, and read these notes. But the other task I have for you is that next week, we're going to start chapter 5 on linear time invariant systems in continuous time, and we'll introduce the convolution, the idea of convolution. So please read that chapter ahead of time. And if you do both the readings and all of this, you will be ready for next week. And as I said, we will likely have a quiz on Thursday. I will post a list of topics that you need to know for that quiz by the end of the day on Friday, and we'll probably talk a little bit about the impending quiz on Tuesday. Okay, I'm going to sign off, and I'll get this video posted, and I'll get the notes corrected before I post those, and I will see you in class in room 212C next Tuesday. Have a good weekend, as I will not see you on Thursday this week. Okay, this ends the program, so I'll stop sharing and I will stop the recording.